Hello, welcome to session number 2, week 5 production strategy. This session will focus on how to build production strategy at an aircraft supply chain and to make a decision about the location of order penetration point or OOP to balance responsiveness and efficiency. Let's go to the next case study on supply chain. Taking aircraft manufacturing at Airbus as an example of this case study by Air Supply. The following case study describes how Airbus implement the ETO or engineer to order production strategy and collaborates with its suppliers using Air Supply. Each time an Airbus aircraft is made, it is the result of assembling a multitude of parts representing a very large volume of orders. Aerospace industry assembly line is flexible to assemble different air transporters such as aircraft, helicopters, and satellites. Parts for manufacturing are coming from multiple suppliers from all over the world. Most of them are quite complex and need to fulfill highest quality standards. Each time delay can cause very high costs. Therefore, it is essential that all suppliers involved in the manufacture of an aircraft have a real-time visibility of the progress of demand and inventory to adapt to fluctuations and changes of customer requirements. If so, it is essential for customers and suppliers to have a common tool that will enable them to better collaborate and to gain visibility of a demand as well as inventory. Each aircraft is practically one of a kind. One of the reasons why commercial aircraft are all configured differently is that the ordering airlines wants to differentiate themselves from their competitors. The easiest way for passengers to spot these differences is by looking at the seats and entertainment systems. With 75%, the value added by external suppliers in aircraft manufacturing is relatively high. A single long-range aircraft is made up of around 4 million individual parts, supplied by companies of many countries. Even at the final assembly line, workers are putting together components originating in at least 4 different countries. Fuselage section and the vertical stabilizer come from Germany, the cockpit and central fuselage section from France, the wings from England, and the horizontal stabilizer from Spain. Where the engines come from depends on the customer preference. The task is made even more complex by the generous length of time Airbus gives its customer to submit their final wishes, including lead time. Manufacturing takes around 2 years, and Airbus accepts customer change requests up to as late as 6 months before delivery. The challenge in aerospace industry is that due to highly customization in manufacturing an aircraft, therefore collaboration with suppliers begins only a few months after the order have been received. Delivery dates are coordinated with suppliers at weekly intervals on both the capacity planning and order levels. The production of components begins before the date on which the customer is able to request the last modifications. Final assembly itself takes around 1 month. This intensive process of coordination with suppliers is managed by Air Supply. Okay, now how the collaborations managed by air supply look like in concrete terms? The first step of the collaboration is that calculating the future demands via the Airbus ERP system. This always takes place at the weekend. On the following Monday, the Airbus order officer checks the generated demand planning, and the next step is the approval of the requirement planning and transmission to the suppliers via air supply. The supplier now checks whether he can provide what is needed by Airbus. If the answer is yes, he sends his confirmation. If the answer is no, he can use air supply to propose alternative quantities and delivery dates. The order officer at Airbus then checks the supplier's proposals and accepts it. The collaboration process has now been successfully completed, and the data is transferred back to the ERP system at Airbus. It is evident that it would not have been possible to conduct this process by exchanging messages in conventional electronic data interchange or EDI format. The rules required to logically represent these collaborations are not provided by classical ERP systems. This is why the entire set of logical rules governing collaborations has been moved to the cloud. The ERP systems simply process the result of the collaborations. From the system architecture perspective, the solution is embedded in supply-owned cloud infrastructure. This is made up of central components that control registration of companies and users. At the current time, around 8,000 companies from over 70 countries are using supply-owned solution. From supply-owned case study, we know that coordination in supply is necessary for complex engineering projects under ETO strategy. After all, finding an appropriate production strategy depends on how much we can invest in providing production responsiveness by taking advantage of having less inventory level or vice versa. That is by providing more stocks, by taking advantage of having a higher level of production efficiency. In Airbus case, it is critical to find an appropriate OPP or order penetration point to minimize total supply chain cost, to respond to customer demand optimally, and at the same time to minimize idle capacity in manufacturing plant. Therefore, it can be observed that the two critical issues in implementing an order penetration point or OPP concept are efficiency or leanness and agility or flexibility. OPP divides the supply chain processes into two categories based on whether they are executed in response to a customer order by using MTO or make to order at downstream part, which is pull processes, or in anticipation of customer orders by implementing make to stock or MTS in the upstream part by using push processes. Pull processes implemented in agile supply chain are initiated in response to a customer order. The advantage of the downstream part are responsiveness and a high degree of customer-oriented product individualization. On the other hand, push processes in lean supply chain are initiated and performed in anticipation of customer orders. The advantage of the upstream part are the economy of scale by consuming low manufacturing and transportation cost, And also because the upstream part has high level of inventory, can create flexibility and therefore can shorten the supply lead times to the downstream part. Although recent literature focuses extensively on the lean versus agile issues, there is a lack of quantitative analysis methods to support the managerial decisions on the locations of order penetration point. In order to develop a quantitative analysis tool to support supply chain managers in their decisions on where to determine the right order penetration point location in the supply chain, we suggest setting the MTO and MTS, or make to order and make to stock views, against each other for full leanness, meaning make to order, and full agility, or make to stock considerations. In the proposed model in front of us, we consider two strategies: make to stock and delivery from a general inventory holding unit, or make to order, introduction into the agile part downstream of the general inventory holding unit. We follow an assumption that in the upstream part of the supply chain, the processes are designed to be lean. Downstream, the processes are designed to be agile. Furthermore, the model allows the OPP, or order penetration point location, to be determined by a set of technological constraints and economical goals. Therefore, different order penetration point, or OPP, locations can generate different supply chain structures. Okay, let's go to our model. The model assumes that the introduction of the agile supply chain part in downstream of the OPP leads to an increase in both flexibility and cost. As such, the model proposes low sales-based treatment of the OPP location, determination similar to the low sales approach to inventory management. The order penetration point location can be determined through a proven comparison of MTO and MTS strategies. This comparison commonly used in many literatures. With regard to the above mentioned assumption, a quantitative estimation of the order penetration point locations can be found by relating the strategies to each other. For instance, an order penetration point location index can be calculated at different stages of the supply chain according to the model on our slides. Now let's go to our example here. We consider a supply chain where 4 potential order penetration point location corresponds to the following strategies: MTO, ATO, CTO, and MTS. For instance, from suppliers delivered to the manufacturing plant using make to order, and therefore the time to deliver takes about 1. It can be 1 hour, 1 day, 1 week, or 1 month. And then in the manufacturing parts, the supply chains make details, and from that details or spare parts, they assemble to make modules. And delivery from each modules to be assembled into final products using assemble to order strategies, and it takes 2 days. Let's assume here the time unit is in days. Next, the product sent to packaging section to be configured with a packaging box, plastic wrapper, user manuals, cables, etc. And it takes 4 days. Considering all parameters used in the previous slide equation, we have different OPP index for different OPP locations. For instance, for MTO, the D index is minus 3.11, for ATO 0.14, for CTO 3.39, and the most attractive one, that is MTS, 6.65. And now, what it implies? Let's see from our table in this slide. For instance, here, what is the meaning of KA and K? That is the sensitivity of customer to customization. And we can see here that customer prefer a more standard product than customized one. And therefore, customer is less sensitive to the increase of responsiveness. And the second, if we look at the array, it shows that due to lower level of revenue from introducing agility and lower investment in the general inventory holding unit, therefore MTO strategy is less attractive as compared to ATO, CTO, and MTS. Now we have the following questions. First, propose the OPP location and recommend a manufacturing strategy. I think we have answered these questions by looking at the previous table. Second, explain the push and pull view of the processes within the supply chain. Third, explain the basic trade-off between responsiveness and efficiency of the supply chains. And finally, explain meaning of the coefficient Ka and K, which we have already answered. Now we go back to the case study of Lenovo and Dell. For that case study, identify basic stages in the value chain which are described in the case studies, and then explain interconnection between production and distribution strategies at Dell and Lenovo. Third question, compare MTO and MTS strategies of both cases. Fourth, describe advantage and possible limitation of VMI at Lenovo. Fifth, for supply chain on case study. Now we back to our case, the latest case study. What benefit of air supply for supplier collaboration can you identify? And finally, describe advantages and risks of ETO production strategy. Okay, these case study questions ends our study in production strategy, and see you in week number 6 in the next following session. Thank you.